Okay, for what we have in problem number 4, we're looking at the sum of the second order derivative of x and 9x equal to the cosine of 5t. And we have, for the initial conditions, we have that x naught is equal to 3 and the x prime naught is equal to 1. And rewriting what we have here in terms of Laplace transforms, so we have with second order derivative, okay, we have, again, with our algorithm, this translates out to s squared times the Laplace transform x of s minus 3s minus 1. So we have both x naught and x prime naught to be non-negligible values. And for the Laplace transform of 9x, okay, this be 9 times the Laplace transform x of s. And we have for the Laplace transform of the cosine of 5t, we have s all over s squared plus 25. And rewriting what we have in this equation in terms of what we have for the Laplace transform equivalence. Okay, again, we have this equation upon substituting, and as we combine our Laplace transform of x terms, okay, we have the coefficients s squared and 9, and as we move 3s and 1 to the other side to join with s over s squared plus 25, upon combining what we have on the right as one overall expression, okay, we had the polynomial to turn out to be cubic all over s squared plus 25, and isolating what we have for the Laplace transform x of s. So we have 3s cubed plus s squared plus 76s plus 25 all over the product of the quadratic factors s squared plus 25 and s squared plus 9. And taking what we have and writing this ratio in terms of partial fraction decomposition. So again, we want to maintain a 1 degree difference between the denominator and the numerator. And again, so the numerator, okay, we're going to have as a linear expression in s. So we have as plus b over s squared plus 25, and we have cs plus d all over s squared plus 9. And we have, upon clearing out the fractions, upon multiplying everything out by both s squared plus 25 and s squared plus 9. So I have this equation set up so as and b are multiplied by s squared plus 9, whereas cs and d are each multiplied by s squared plus 25. And setting up a system of 4 equations. Again, you have 4 unknowns, which will require 4 equations. And I have this particular setup, and we have just lining up. So I've just set s to 0, 1, 2, and 3, and plugged into s at each stage for all the terms throughout in the above equation. And I came out to these values. Okay, so looking at expressing what we have in terms of a matrix. Okay, so we have, again, just taking what we have for the A term, B term, C term, D term coefficients, and the far right column we had to be in reference to what we have each equation to be set equal. And we have from the reduced row echelon form, A comes out to negative 1/16, B is negligible, C is equal to 49/16, and we have D is equal to 1. And just going back to what we have for the partial fraction decomposition, so we have with as over s squared plus 25, that would be negative 1/16 of s over s squared plus 25. Again, b is negligible. And we have with cs plus d, we have for cs over s squared plus 9, we're going to have 49/16 of s over s squared plus 9. And d, we have 1 over s squared plus 9. And so we have for the Laplace transform x of s. Okay, so you have negative 1/16 of s over s squared plus 25. You have 49/16 of s over s squared plus 9. Now for 1 over s squared plus 9, if I put this in the form of k over s squared plus k squared, now your k value is going to be at 3. Okay, but now we have 1 at the top, and think of 1 as being like 1/3 of 3. So I'm extracting a fraction with 1/3 and just setting this up whereupon I can attain the solution of x. So taking the Laplace transforms here and applying the inverse. Okay, so we have, in this particular case, we have the inverse Laplace transform of s over s squared plus 25. This would be the cosine of 5t. S over s squared plus 9 would be the cosine of 3t. and 3 over s squared plus 9. If you have a constant over the sum of squares, you come out to a sine expression. In this case, you have the sine of 3t. And we have with the fractional coefficients at the front, it turns out that for x of t, we have negative 1/16 of the cosine of 5t plus 49/16 of the cosine of 3t plus 1/3 of the sine of 3t. For number 5, okay, we're looking at x double prime plus 16x is equal to the sine of 7t. And we have supplied with the initial conditions x naught is equal to 2 and x prime naught is equal to 1. And translating what we have in the terms to their Laplace transform equivalents, okay, for x double prime and the initial conditions laid out, we have s squared times the Laplace transform x of s minus 2s minus 1. For the Laplace transform of 16 times x of t, we have 16 times the Laplace transform x of s. And for the Laplace transform of the sine of 7t, we have 7 over s squared plus 49. And putting these terms in their respective places, we have this equation in the setup. And as you look at isolating the Laplace transform x of s terms, we can gather the coefficients where we have s squared plus 16. And then with s7 over s squared plus 49, if I add 2s and 1 to this term and combine as one overall ratio, we have once again a cubic polynomial over a quadratic expression. And so we have for the Laplace transform x of s, you have this cubic polynomial over the product of s squared plus 49 times s squared plus 16. So we're back in the terrain of setting up partial fraction decomposition where we have both factors in the denominator are quadratic. Okay, so I have as plus b for the first numerator, and again I have cs plus d for the second numerator, and clearing out the fractions. Okay, so I have the initiation of what we're going to have for the what will be a system of 4 equations, and so just choosing the values again of 0, 1, 2, and 3, our 4 smallest whole numbers to plug in for s, and I have these particular values to line up. And again, setting up as a matrix where we have at the front the A term coefficients, second column B term, third column C, fourth column D. Last column you have the values to which each equation will be set equal, and applying the reduced row echelon form. So you have A is negligible, B is at negative 7/33, C is going to be at 2, and D we have at 40/33. And going back to the partial fraction decomposition setup, so again, A is negligible, but for our B over s squared plus 49, that will be negative 7/33, the reciprocal of s squared plus 49. And we have with C, s over s squared plus 16, C at 2. We have 2 times s all over s squared plus 16. And we have with D over s squared plus 16, so that will translate with D at 40/33, we have 40/33 times the reciprocal of the sum of s squared and 16. So we have for what we have for the Laplace transform x of s. So again, with the first expression, okay, we have 1 over s squared plus 49. And if I put this in the realm of where we have k over s squared plus k squared, well, our k value is going to be at 7. And so just rewriting this set of terms, okay, so we'll have negative 1/33 of 7 over s squared plus 49, and we have plus 2 times s over s squared plus 16, and we have, again, to line up where we have k over s squared plus k squared. If k squared is 16, well, our k value is going to be at 4, and just rewriting, okay, so you have like a product of 40 and 1, which is 40, and having k at the top of the sum of the squares, we had 4, okay, and like 4 into 40 will be 10 times. So I'm going to have 10/33 of 4 over s squared plus 16. And now we have with the setup where I can solve for x using inverse Laplace transforms. So we have for x of t, we have negative 1/33 of 7 over s squared plus 49. Now that would be the sine of 7t. And we had next term, we had the inverse Laplace transform of s over s squared plus 16. And this would be in reference to the cosine of 4t. And the last term where we have the inverse Laplace transform, 4 over s squared plus 16. So we're going to have our expression nt to end up as the sine of 4t. So we have in the solution, we had the x of t is equal to negative 1/33 of the sine of 7t plus 2 times the cosine of 4t plus 10/33 of the sine of 4t.